Hello and welcome to our talk on fairness in machine learning. I'm going to be sharing slides as I go. However, if you want to take a look at the slides yourself or peek ahead or go back over any of the slides, they're fully available at this URL, predictiveanalyticslab.com/presentations. And then if we look under the summer school, we have the link to the lecture, and also as a little spoiler alert, there is an exercise as well that we'll be looking at doing towards the end. So if we go ahead and take a look at the lecture. So hello, I'm Oliver, and my colleague Thomas is also on the panel. We're from the Predictive Analytics Lab at the University of Sussex. We're going to be presenting together. We'll be doing so by, I'll take the first part, Thomas will take over for the second part, and then when we come back for the second set of lectures, we'll do a very similar process again. So just to cover roughly what we're going to talk about, these lectures are in two parts. The first one, we're going to have a brief introduction to who we are and also some of the notation that we're going to be using, just so a quick summary. Then we're going to talk about fairness and why hopefully you should all care about it. And then we'll talk about some of the definitions of what is fairness, followed by some approaches on how to enforce it. In the second part, so later on this afternoon, we'll be talking about transparency. That's something that we've been working very recently on. We'll also be talking about causality and counterfactual fairness, which I understand a lot of the lectures in this summer school have spoken about causality, so hopefully that should be a good one for everyone involved. And then lastly, we're going to speak about one of the toolboxes that we've been using and working on called FML. There'll be a link, there's a link to this in the exercises at the end. So we've put that at the end, so if we rattle through the slides really quickly, there'll be more time for that. And if the slides take a bit longer, or if there's more questions, that's absolutely fine. You can have it as a take-home exercise. So one of the things we should probably talk about is what this set of lectures won't cover. Fairness is a very difficult problem, and unfortunately we're not going to solve it in one set of lectures. And to be honest, although a lot of progress has been made in this field, we tend to solve very specific areas of what fairness means in specific contexts. We certainly don't make any claims to broadly solve fairness problems. That's an active research area, and hopefully this piques your interest and makes you interested enough to want to pursue this research area further. One of the things that we want to, or we like to do, is to give you the take-home messages. So if you have to leave early for any reason, it is a Friday after all. And also just so you know what's coming up, this is what we want you to take away from these lectures, that fairness is the main specific, the main problem really. So fairness in the world of hiring will not be the same as fairness in the world of medicine, for example. Getting to know the domain and getting to know the domain expert is vital. The next thing is that if you don't think about bias and unfairness in algorithms and machine learning, it will definitely come back to haunt you, and you will not have a good time. The other one is that accuracy that we all focus on so much in terms of our models, that only really tells part of the story. And hopefully as well, you take away from this that fairness is an active and exciting research topic. Speaking of which, we should advise that we're hiring. So if you like the talk that we're giving, and at the end you think this is cool, I'd like to know a bit more about this, visit this URL, tinyurl.com/sussex-phd. We've got 6 PhD positions working on algorithmic fairness, so maybe check it out. So let's start right back at the start, and this is probably going to be all things that you already know. but it helps just to make sure that my notation and Thomas's notation is the same, that everybody else understands, and we're not making any confusing points. So machine learning is broadly just the ability to learn from looking at lots of data without being explicitly programmed. We talk about input features X, and we talk about class labels Y. We're mostly dealing with classification problems in the world of fairness. So we're going to, just for this ease and simplicity, sake of simplicity and ease, we're going to stick with the classification setting for this talk as well. Although obviously classification can be multi-class and can certainly go to more than binary, we're going to also stick with the binary classification setting, so where our class label is 0 or 1. Again, this is mostly to do with simplicity, and stop our slides and the math on our slides going on for a lot longer than it needs to. So in terms of our classification, we're looking to train a function f, and we'll use that notation throughout, that maps some x to our y, our observed label, and we also have our prediction of that as well, that being the output of the function. F can be implemented as either anything really, a neural network, an SVM, a decision tree. You could even have it as a coin toss, although I wouldn't expect your accuracy to be very good in that case. And then in terms of training data, we just have pairs of data. This should be IID. As we expand on this talk, we'll introduce a third variable to this, which is S. So X being our input features, Y being our class label, and we'll also introduce S to this pair to make a triplet. S referring to a sensitive attribute. This being just a class label, essentially a class label, but not labeling the class. So an example of a sensitive attribute would be, for example, gender or race. It's something that is a label about an individual that is sensitive in both the eyes of the law and, broadly speaking, morally or ethically can be sensitive to. Generally, we're looking to build a model that works well on unseen data, as you all know. So we try to gather training data that is similar to our deployment setting, where we're actually going to use a model and hope it generalizes well. However, unfortunately, this is not always possible. If we make predictions, then if we make predictions on data that's vastly different from our training data, we're going to expect that the model will perform poorly. That shouldn't be massively a surprise to anybody, because if the training data doesn't describe our deployment setting, then clearly we're not going to expect the deployment setting to do well. Unfortunately, when it comes to practicalities, we don't always have choice on the ideal training data. Finding labeled data to match our task can be a very tricky challenge. Often this leads to us producing proxy labels, so labels of outcomes which don't exactly match our task, but we feel could do a good enough job. This can often be a root of many problems. So we've spoken broadly about machine learning and what the aim is and what it's doing, and where is it being used. So outside of the ones listed on the slide, machine learning's had an awful lot of success in telling us a lot about situations where we don't necessarily have any judgment to make, but we can just find the patterns. So in terms of meteorology, in terms of playing Atari games, machine learning has done very well. It's done so well, in fact, that people want to use it on systems that are more decision-based. And ones that are more decision-based usually involve a human. So decisions around hiring, bail, credit approval, and insurance premiums all have a direct consequence to us humans. And that's really where the crux of the problem really starts to be noticed. So clearly there are problems with this, else we wouldn't be giving this talk. You may have seen headlines recently. So this is one from a few years ago about ProPublica, that ProPublica reported, called, well, their topic is called machine bias, but this is about a recidivism prediction software used in the United States. Recidivism is trying to determine, will somebody who's released from prison go on to commit another offence? So it's used in bail decisions. So if somebody's up for bail, the details get passed into a computer, and this will tell you how likely somebody is to reoffend or not. The sensationalist side of this is that they will say that if you put in two people who are exactly the same, the only difference being race, so you had, let's say, Bob and Andrew, they're both exactly the same. The only difference is the one attribute. One is white, one is not white. The white person will be labeled as not predicting a crime, whereas the person who is labeled as not white will be labeled, the outcome of it will be that they will go on to commit a crime, they will go on to commit recidivism. This is perhaps a little more sensationalist than the truth depicts. There's a kind of a wonderful analysis of this done by Corbett Davis. It's definitely worth reading because it opens the lid on it a little more. You may have also seen a tool that Amazon built, or heard about rather, a tool that Amazon built for screening CVs. The problem with this was that it was trained to predict based on the people they'd hired previously. Now, unfortunately, they'd previously hired predominantly men, and the system learnt to enact this and would actively discount any descriptions of an individual that link to their gender. So, for example, if you put that you were captain of a sports team, you would be rated highly, but if you would be rated that you were captain of a women's sports team, you would be rated lower. This was scrapped very early. This is not something that made it into production, but it did make the headlines, and then hopefully brought it to some people's, well, hopefully in terms of if there's any good that came out of it, brought this issue to people's attention. There have also been other ones. I won't go into more details of this, but there was a report recently in Canada about the use of automated decision-making systems on immigration, essentially passport control gates, and another sensationalist headline about AI-powered sociopaths and psychopaths. These are very, again, kind of sensationalist headlines, but you will see a lot more of this type of thing, particularly with GPT-3 having been taking a lot of the news, the machine learning news recently. Everyone's very impressed with its success, but clearly, if you prime it in the wrong way, your GPT-3 model will produce some undesirable outcomes. So when we talk about algorithmic bias and machine learning, fairness machine learning systems, we say machine learning systems, when they're making decisions that affect humans, certainly, we need them to be fair. The problem is, though, that by default, machine learning systems tend to be biased in some way. And although I've got some questions built into here, they're certainly rhetorical. I'm not expecting Slido to start pinging off, although we're using it. So if anybody wants to use it at any point, you're more than welcome. And why are machine learning systems biased by default? Well, realistically, the world is a very complicated place. The data is unlikely to be perfect right from the start, and the developers often arbitrary decisions where you don't really think about what the decision that you're making and the impact it will have, because you don't necessarily realize it. That will go on to have some downstream impact. There's also a problem that business goals, so any of you who are working as machine learning engineers or research scientists in the out in the corporate world, you will know that business goals don't always align with fair behavior. And when I say fair, I just solely mean in terms of our statistical notions of fairness that we will discuss later on in this talk. So because they're not biased, because they're biased by default, we have to certainly take this into account in any of the work that we do. So broadly speaking, the problem can be divided into a couple of categories, and certainly both types of these biases can appear together. But we have bias stemming from the training data, which is a very large topic and is something that I spend a lot of my time looking at. And there's also bias stemming from the algorithms themselves. I think when it comes down to this in the real world, people are often very quick to jump on the first one and say that, yes, well, bias solely comes from training data. Therefore, the problem is that I don't either have enough data, or that the problem is with the data, not with the complex and expensive model that I've built. It's kind of a way of not trying to tackle this problem head on, rather than trying to offset it somewhere. There was, if any of you follow machine learning Twitter, you will have seen that this debate has been somewhat prevalent recently. Realistically though, bias does also stem from the algorithm itself. You'll see some notions later on of fairness and measures, and I'd encourage you to play around with train a simple model, then change the regularization term, and then watch the effects of the fairness of the model that you produce. You will see that it is not consistent, and this should hopefully give you some indication that decisions that you're not necessarily intending to cause any downstream problems can do if they're not monitored. So first, let's talk about bias training data, because it is a problem. So I quite like this term, or this analogy rather. In databases, we have GIGO, for those of you who have done your databases research, so your databases modules at university. GIGO stands for garbage in, garbage out. If you put garbage into your database, it's just going to spit garbage back out for you. Machine learning has kind of a similar an acronym of BIBO, which is if you put biased data in, you will get a biased model out. This is generally true. Machine learning models just tend to learn what's in the data, what's in the training data. So if your training data isn't representative in some way, or there's undesirable patterns or even spurious correlations within your training data, then your machine learning model as a pattern recognition tool is going to be very, very good at recognizing these patterns and exploiting them. So let's take a look at this. There was a paper recently, Women Also Snowboard, which is a fantastic name for a paper, but the task is to generate descriptions based on images. So this is an example from a paper, or from a very similar paper, where you have an image and we want to take a look at the task. You can see that in all of these images, there's somebody in the kitchen, and they've got several roles and the values that those roles can take. So if we start at the leftmost one, the agent is a woman. The food this model has determined is pasta. We're heating on a stove with a spatula in a kitchen. And if we go across, we can see that actually something has been labeled incorrectly. We've got someone who is clearly, clearly has pattern baldness, male pattern baldness, and would probably identify as male, be labeled as a woman. And we're trying to work out kind of what is going on here. In the paper, they identify that actually majority of examples of people in the kitchen are labelled as women, and the model learns that some shortcut to label this. So what we really want is, instead of looking at the kitchen to determine who's in there, we want something that actually looks at the right thing. So one of the things is we can be wrong for the right, well, we can be right for the wrong reasons, and we can be just wrong generally. If we take a look at this example on the left-hand side, we've got somebody sat at a desk with a computer, and this captioning program has looked at it and said, based on the fact that there's a computer, I'm labeling it as a man sitting at the desk, which is obviously incorrect. Certainly, we'd want the model to be taking a look at the actual person that we're going to be making a decision about, rather than the things around them. So in the second one, the model is constrained to look at the person, and it gets it correct. On the right-hand side, we've got a very similar thing, but it's perhaps a little more difficult to spot from the outset, because the model was right. This is a man playing with a bat and ball. However, it was right for the wrong reasons. It took a look at the bat and then immediately said man, rather than going on and taking a look at the person that you're trying to describe. So really what we want is the algorithm to take a look at the person they're predicting the gender of. I should stress with this, though, that we're using this as an example. I know that in recent works, tasks that are predicting of gender generally are being looked at with some more scrutiny as to whether this is a necessary task to do in the first place. I think it's possibly a good time to interlude and say that absolutely, if you're being asked to do something, it's always a good idea to question if this isn't a necessary task to do. Yeah, just something to think about. And certainly, as we've said here, if the gender cannot be determined in this particular task, if you've determined that we should be doing this, and it's important that our model does it. If we're unsure, then the output shouldn't be, let's just guess, let's say that we're unsure. So in the previous example, we had a problem that our some data was underrepresented and some was overrepresented. This is an example of sampling bias. However, we have other situations as well where the underlying data is just plain wrong. This can easily happen when you're asking people to fill out forms. Humans have a habit of either lying sometimes, or misunderstanding questions, or trying to exaggerate in some way. So what we want to do is make sure that we enforce some sort of fair outcome. So one thing we could do is to say, right, treat all groups the same. A group being, for example, male and female being two groups, or it could be race categories or religions, but let's just call these groups. And what we want to do is treat all groups in the same way. So how do we define a fair outcome? Well, this is the source of many a research paper, but let's start with the very simplest definition and go from there. So in our simplest definition, let's assume that we've got some task of trying to work out should somebody be hired or not hired. So class label 1 or 0. And let's, just for the sake of argument, have two races, a blue race and a green race, which populate our sensitive label S. So S0 corresponding to the blue race and S equals 1 corresponding to the green. In our training set, 20% of blue applicants were hired, 80% of green applicants were hired. Was this a fair outcome? Well, it's hard to say. So in terms of statistical parity, this is our first notion of fairness, and also, incidentally, the simplest. Statistical parity says that regardless of the sensitive attribute, the probability of a positive outcome should be the same. So, yeah, meaning the probability to get a positive prediction is the same for each group. So whether you belong to, in the previous slide, the blue race or the green race, the probability of a positive outcome should be the same for either, regardless of the fact that in the training set we've got such a disparity. Again, concretely, what I've just described. In the hiring example, though, that we've just spoken about, the same positive prediction for both will be that we hire 50%, or we predict to hire 50% of both groups. This will clearly have a problem, because if we go back, we can see that 20% of blue applicants were hired, 80% of green applicants were hired, and if we're going to say we should hire 50% from both groups, then that's going to have a massive effect on our accuracy. Accuracy is not going to be a good measure for this. The only way that we can make this work is to have our classifier purposefully misclassify. This isn't surprising at all, because our sampling and bias occurs within our underlying training data, so we have to take that into account. But this introduces something called the fairness accuracy trade-off, where if we're comparing against our underlying data and we're saying that our underlying data is the ground truth and cannot be questioned, then the moment we try to deviate away from that and have a model that, assuming that our model is a non-perfect predictor, we're going to have some trade-off around fairness and accuracy. So if we satisfy our accuracy, then our fairness will be poor, or our fairness measure will be poor. But if we satisfy the fairness measure and don't take into account accuracy, then we're going to have a classifier that it doesn't work very well. So a very easy way in this situation to get a very fair classifier would just be to have our f, our function that we're learning, just be a coin flip. This will produce a positive prediction rate of around 50%, regardless of the input. The problem is, of course, that it's going to be pretty useless. So there are situations, so you might say, well, okay, maybe statistical parity isn't the right thing to use, full stop. I'd say don't necessarily write it off. It is a valid notion of fairness, and there are some situations where this is absolutely the right measure of fairness to use. It is simple. It does obviously have some trade-off with accuracy, however, and there are some more sophisticated criteria possible. We're going to go into one now, and Thomas, I think, will come in and talk later about causal graphs, and you might be able to draw your own conclusions in there about some more sophisticated criteria. However, absolute statistical parity is a completely valid notion of fairness, and is one that is good to measure. So that's some bias introduced by that can be a measure of data, bias introduced by the data. And there can also be bias introduced by the machine learning algorithm itself. So again, consider the setup that we had previously. The only difference this time is we're going to explicitly say that the composition of the data set is 50% blue, 50% green, but 20% of the blue have a positive outcome, and 80% of the green have a positive outcome, which is as before. We're also adding we're adding some features here. So our input features are some SAT score, and also the race is going to be registered as a input feature. So our inputs are going to be SAT score and the race. We're going to have some model, and then we're going to have a prediction. Now, the data set is heavily skewed, but let's just kind of ignore that for now, and some of the problems that that can introduce in itself, and we'll just talk about it in terms of just the algorithm. So a really effective way in this model to get good accuracy with good values, for example, if you've got weight decay on a network, and you want to penalize your model for being complex, so a well-regularized model, you could learn a very, very simple rule, which is ignore the SAT score and don't take that into account whatsoever, and instead just have a race predictor. You're given the race anyway, you just return that feature as the output. So your model will learn that this is a very easy pattern to find, and it will also learn that if it does this, it will get reasonably good accuracy. So you'll get 80% accuracy for the blues, you'll get 80% accuracy for the greens, 80% accuracy overall. It's very much simpler than learning the complex relationship between SAT score and whether somebody should be hired or not. So the data set was already skewed, but then the algorithm has jumped on this and made it worse. It's found a pattern that maybe wasn't intended at all. It's just exploited the pattern that was there. Someone once described to me that machine learning models are a bit like water in terms of they find the shortest path from one place to another. And here our model has done something similar. It's learned that, aha, if I just return this input feature, I will do relatively well. This might seem a bit made up and a bit of an extreme case, but versions of this absolutely do happen. And what's more is they create a feedback loop. So if you had this system in place for a number of years, all that would happen is, as the new data comes in, it would just completely reinforce everything and all the assumptions that the model has previously made. When I mentioned at the start that if you don't take into account fairness and bias in your machine learning models, they will come back to haunt you. This is certainly one of the examples of this feedback loop that you can accidentally create. So how can we measure this in some way? So we don't want the algorithm to be lazy about a subgroup. We want it to make equally good predictions across all of our groups. So this is a notion of fairness called equality of opportunity that forces this. This is very similar to statistical parity, apart from cleverly, we also condition on the actual recorded output as well. So the probability of predicting a positive outcome, given that the true label, the reported true label is positive, it should be the same for groups, for all groups, which in practice means that we try to balance the true positive rate across subgroups. There is a slightly more complex version of this called equalized odds, where you don't only balance the true positive rate, but also balance the true negative rate across groups as well, which is also a completely valid notion of fairness, but is somewhat less used than the equality of opportunity. So both equality of opportunity and equalized odds make the assumption that the trained data is correct. And they're also, one thing to note about them is they are only measures with you assuming that you have a non-perfect predictor, which is the general case for machine learning. Unfortunately, a perfect predictor should be treated with supreme caution because it's a bit like when you write code and it works completely fine the first time. You should be suspicious. So unfortunately, a random classifier also does well. Again, we've got this problem with the fairness accuracy trade-off. So yeah, achieving equality opportunity or equal results at a low accuracy is very easy, but that's always the challenge, is trying to find the balance on that trade-off. So we've spoken a bit about bias in both the model and in the data. We should probably speak roughly about fairness definitions more broadly. So we've got discrimination laws that exist. There's the concept of direct discrimination. Generally, this is realized in terms of intent. So when we talk about it in terms of machine learning, one of the things we try to make sure that we do is not make decisions where the sensitive attribute is an input to the model. So we're not actively taking it into account. And then direct discrimination is respect to consequences, and that has a broader tie to the definitions that we've just spoken about previously. Yeah, so where we try to talk about enforcing equality or some notion of equality, such as statistical parity or equal opportunity on the outcomes of these groups. So these are some statistics-based notions of fairness. We've spoken before about statistical parity and equalized odds and equal opportunity, but there's also calibration by group is another measure. I just wanted to dig into these slightly more. The reason is that these are, if you're going to take one thing away, it's that if you're, from this talk, is that if you're going to be making any decisions or you're building a system that's making decisions with regard to people, you should definitely be measuring, your system based on these concepts. Not all of them might be applicable to your current setup or to the domain that you're deploying in, but you definitely want to make sure that you've at least considered them. So let's talk about them a bit more. So going back to statistical parity, this is labeled as an independence-based notion of fairness. And we're going to talk about this as independence-based. There's another one coming up called separation-based and sufficiency-based. These definitions come from the FAIR ML book, which is written by 3 wonderful authors, and it's fully available online. I really do recommend checking it out. It's, if you search for FAIR ML book, it's a wonderful resource, and we try to make sure that we use the same language as from that book, because it provides good consistency throughout. So yeah, statistical parity being independence-based notion of fairness is classified as independence because we want our sensitive label to be independent of the predicted class label Y. So that's the Y with the hat on. Again, in terms of math, we can see that our probability of positive outcome should be the same for our 2 sensitive groups, and this can extend to multiple sensitive groups. In terms of optimization, this is kind of a challenge actually, because when you get to multiple groups, in enforcing equality over so many is a combinatorial problem, and it's something that there's a lot of research going on in terms of taking into account more than a binary sensitive attribute. One of the problems we've got as a field of fairness in machine learning is that we don't have fantastic measures for a non-binary setting. Something that I know my colleague Thomas has been thinking about a lot. Sorry, just taking a drink. Next up, we have equalized odds, which we've spoken about already, and equal opportunity. These are both separation-based notions of fairness. The term separation, because if you drew them as a graphical model, you would see that S and your prediction of y would be separated by the true label. Again, this is very similar to statistical parity, but we're just conditioning on the true label as well. We're conditioning on the true label being positive in equality of opportunity, and just on the true label generally in terms of equalized odds. It's kind of a subtle difference, but that's the difference between the two. And lastly, we have calibration by group. This is a they call it sufficiency-based notion of fairness. This is kind of this might seem a little strange, but you'll see in an example coming up why this completely makes sense in some situations where you want your sensitive label to be independent of your class label, conditioned on the predictions. So in terms of what this really means, if we take a look here, it means that your prediction, between the prediction and the report and the outcome, this shouldn't be affected by the sensitive attributes at all. There's a university example coming up in a couple of slides' time. You'll see this and you'll go, well, of course, that makes complete sense in that situation. So which fairness criteria to choose? We've just listed out a few. Why don't we just have all of them, right? If we're fair with regards to them, with regards to all of them, then we're fair overall, right? Well, unfortunately not. If we have this independence-based notion of fairness, such as statistical parity, and separation-based notions of fairness, such as equality of opportunity, then for them to both hold at the same time, then the only situation, well, in the binary case anyway, binary classification case anyway, the only way that this can hold at the same time is if our sensitive label is just independent of our true class label, so meaning that our data is pretty fair already, or that our prediction has absolutely no bearing on the between the prediction and the true label. So we just have a random predictor. Similarly, sufficiency can hold with can't hold with either of these at the same time as well. So you really have to kind of choose, and that can be a difficult thing to do because, as we've said, in different contexts, one version of fairness might just be completely the wrong thing to do. And I kind of want to illustrate it with this university example where, well, let's run through the example and we'll talk about it a bit more. So consider a university where we're in charge of administration, the bit of the university that everybody wants to be in charge of, right? We've got a system where we can only accept 50% of our applicants. We've got 10,000 applicants female, 10,000 applicants male, and we've been tasked with regard to being fair to gender. So without knowing anything else at the moment, we could see, right, well, in terms of statistical parity, we're probably just going to accept half of each. But really, this isn't enough information. So let's find out some more information about what's going on. We've got an acceptance criteria that is highly predictive of success. 80% of those who meet the acceptance criteria will successfully graduate, and only 10% of those who don't meet the acceptance criteria will successfully graduate. So what does this mean? This means that if I've applied for university and my high school grades met some threshold, then I'm likely to go on and be a success at university. And if my high school grades didn't meet some threshold, then I'm unlikely to go on to be a success. This is a very oversimplistic setup. Please don't read into it that I'm saying anything I don't intend to say about people who didn't do well at high school and their potential for success. So one of the things with this that some of you will have noticed is we're not really doing any machine learning here. We're just saying we've got some criteria already that's set in stone. But as I say, this is meant to be a very simplistic example, so we can just try to get a feel of these different notions of fairness in practice and what that means and how there can be different outcomes based on this. So again, please treat this with a pinch of salt. It is just meant to be an illustrative example. So as we're a good university, because of course we are, we have lots of applications from people who don't meet the acceptance criteria. So 60% of our female applicants, so 60% of our 10,000 do meet the acceptance criteria, and 40% of the 10,000 male applicants meet the acceptance criteria. And we can only accept 50% of all applicants. So what should we do? So let's start off with looking at this in terms of a truth table. So for our female applicants and our male applicants, we've got those who were accepted and those who weren't. And we've got those who actually graduate and those who don't. For anyone who wants to check my math, you're more than welcome to. I was doing this quite late when I put this together, so if those are any blatant mistakes, please let me know. So if we go on and just look at, let's just accept the numbers that we've got. So we have the very lucky situation that a 60-40 split, we can accept just those who met the acceptance criteria. This would give us these numbers, and this, being our current system, would actually satisfy calibration by group. So the outcome is independent of the sensitive label, conditioned on the prediction. So the fact that they're part of the sensitive group had no bearing on our prediction at all. So we go to our people higher up and we say, well, actually, you know, you're already satisfying calibration by group, and they say, well, is that the right notion of fairness for us? Maybe we should be looking at statistical parity. I attended a wonderful summer school talk where they spoke about this. Maybe we should be doing this. Can you tell me a bit more about how statistical parity would affect our application process? So statistical parity, we just end up accepting 50% of both applicants. Now let's assume that we do this in some sort of clever way, and we take the 50%. We take 5,000 of those females who applied, who had the right acceptance criteria, and we accept all the 4,000 males, plus we randomly select another 10%. So 10% of qualified females are just going to be rejected, unfortunately, and 10% of unqualified males will be accepted. Again, please feel free to look at this over, but roughly we've got the numbers. And we can see that there's been some change. In terms of the previous one, we're now accepting less females, and so the ones who actually went on to graduate have dropped, and we've replaced those 1,000 with 1,000 males who predominantly don't graduate. So we feed this back to our university superiors, who say, okay, perhaps statistical parity isn't the right notion, but I've heard about equal opportunity. How does that affect? How would that affect our administration's process? Well, equality of opportunity is all about balancing the true positive rate across groups. So the true positive rate being the true positive over true positive plus false negative. In terms of our truth table, basically we want the ratio across the top line to be the same. I won't make everybody sit and work this all out with a pen and paper to try and work out what that true positive rate should be. We'll just give you the answer straight off, that 55.5% of female applicants and 44.5% of male applicants should be accepted, giving us a true positive rate of 85% across both groups. So if we look at the top row, the ratio of accepted over accepted and not is the same ratio for both groups. And this is, as we'd expect, a bit close, somewhere between the 50% and the 60% of our calibration by group, and we get somewhere in the middle. That might seem kind of like a bit of a trite example, but hopefully you can see that actually these different notions of fairness and the ones that we decide to use can really produce quite different results. If we had someone who said, actually, we're going to be fair with regard to statistical parity in this setting that is not appropriate for it, we might end up with a situation that can actually make things worse for some groups. Similarly, we can be fair with regards to, say, for example, by calibration, sufficiency, based notion of fairness, and maybe if we're not measuring it, we're not even able to start asking those questions and recognizing that in the first place. So all of those notions that we've just spoken about fall under this idea of group-based notions of fairness. So we're not looking at an individual member of a group, we're only looking at the group as a whole. So we only talk about fairness in terms of male and female, or race groups, or any other groups that people might be grouped by. However, that's not the only notion of fairness. There is a sort of vastly different approach, which is kind of simple at its heart, but as with all things simple, it gets more complicated, and that's this idea of individual fairness. So let's not take a look at the groups as a whole, but let's look at individual members of these groups. Individual fairness simply says that similar individuals should be treated similarly, but this is tricky. What is similar, and in terms of similar individuals, and what is similarly in terms of how they're treated? So you could say, let's base our definition of similarity on some sort of distance metric. This could be Euclidean distance or not, but determining that notion of distance and similarity is very tricky. If anyone has ever worked with distance-based measures before, they'll know immediately that that's a can of worms straight away. And certainly you shouldn't try to make any steps down that progress without talking to someone who knows the domain that you're looking at operating in. So another option might be like kind of pre-processing in some way, and maybe clustering almost in terms of the k nearest neighbors. This is heading towards an approach that my colleague Thomas, who's on the panel as well, has worked on recently. He might speak about this in greater detail later. I'm going to skip these next two slides. So which fairness criteria should we use? We've given several statistical definitions, and we've spoken about individual fairness. The message, we've said it several times throughout, and we will continue to drill this throughout the talk, is that there is no absolutely correct answer to this that we can give. You should certainly speak to a domain expert for your particular domain, whether that's hiring in the medical domain, or in image processing. There is no one-size-fits-all model. I'm going to brief. Actually, no. I was going to say I was trying to work out if I'm doing delayed impact or if we're handing over at this point. I'm going to hand over to my colleague Thomas. Once I work out how to stop sharing my screen.
Okay. Okay. Can you see my screen, Oliver?
Yep, yes, we can.
Great. Okay. I guess I'll go back quickly to skip this slide, right? So, so the idea is to Right. So this is a processing approach to individual fairness, where we first we need a distance metric between samples, as always in individual fairness or similarity-based fairness at least, and then we find neighborhoods of points, and then we check whether the labels are actually the same in those neighborhoods. And they should be, because these points correspond to very similar individuals, and according to individual fairness, then the outcome should also be similar. So the class label has to be the same as the neighborhood. So then we flip those labels if they're not correct. And this is, of course, always a bit weird, like we're just messing around with the class labels. You should only do that if you kind of suspect that the class labels are maybe not correct. And then you feel justified to change them. The other option is to do the individual fairness during training, where you enforce it in the classifier that similar inputs should have similar outputs. So you put some additional loss on the classifier, which enforces, so that the output is similar for similar inputs. Yes, so that's that part. Okay, then to the delayed impact. So this is going a bit beyond normal machine learning now, and considering the whole ecosystem, kind of. So maybe as a machine learning person, you don't necessarily have to think about this, but it's still good to have this in mind. So when we enforce specific fairness notions, and then we actually use a classifier that conforms to these notions, and we make actual real-life decisions with that classifier, then this will, of course, have real-world consequences. And some of them might not be good. So the example that we consider here is a bank which wants to automate their lending decisions. So just automate the process of deciding whether someone should get a loan or not. And if someone receives the loan and pays it back, then it's all good. Then the person who got the loan is happy, the bank is happy, and usually their credit score will go up, their applicant, and that means they can get the loan more easily in the future. Yes, that's the good. The other possibility is, of course, that you give out a loan that's not paid back, then the bank is unhappy, and the credit score will go down, and this will have future problems for the applicant. So what the bank is trying to do is maximize profit. Now, if we ignore any fairness concerns, then this is what the bank wants. So they only want to give loans to people who will pay it back, so that they can get the interest and earn money in that way. So naturally, the bank will not give loans to people who they expect will not pay it back. And if the bank can estimate that accurately who will pay back, then this is not the worst thing to do for the bank, right? So it doesn't harm anyone by doing that if it can estimate accurately who will pay back. But now say we care not only about the bank's profit, but also about something akin to fairness, where we have different subgroups, the blue people and the green people. And again, the bank may take a lazy shortcut and say, we will never give loans to green people. We don't even consider it closely because we're too uncertain or something. And then the credit rating becomes an exact identifier for race, which we would not want. But yeah, we also don't want the bank to give out like just any loan, because that will make the bank go bankrupt and also crash the credit ratings of all the people who can pay back. So in a paper where they consider this, they produce this outcome curve, and you see at beta max util, that's the selection rate that would maximize the profit of the bank. And delta mu, I think, gives the difference in credit score that we can expect. So in their model here, the beta max util does not give the highest expected increase in credit score. That would be at beta star. But we can also see that max util is not that bad. There are much worse choices. Especially if you go beyond beta 0, then, so if you basically accept any loan application, then the expected change in credit score will actually go negative. So this will actively harm people. And the yellow areas are where the change in credit score is worse than what the max util choice would have been. And the turquoise area is where the credit score would be affected better than what the max util choice wants. So that's the area where we want to be. But we have to be careful that we don't shoot over it. Yeah, so these are the areas just explained. And yeah, the relative harm is worse than the max util choice, and absolute harm will actually lead to negative changes in credit score. Okay, that concludes the section on fairness notions and definitions. And now we're going to look at how to actually enforce them. Okay, so first we can split up the approaches into pre-training, during training, and post-training. We start with the pre-training examples. So pre-training means that we somehow pre-process the data and then just hand the pre-processed data to a normal classifier that's not fairness aware at all, which will just learn from that pre-processed data and do some predictions. So all the fairness related stuff happens in the step before training the classifier. when we produce the fair representation. So the fair representation consequently needs to be like every trace of correlations between S and Y need to be removed. So it has to be that when we learn to predict Y from this, there's nothing about S in there anymore, nothing about the sensitive attribute in there anymore, so that our classifier will come on safe, fair. We have four examples here, which I think I will go into a bit of detail. So there's the paper from Zemo et al., which was the first, I think. Which, yeah, they all usually use adversarial approaches where you have one part of a neural network that produces a representation and another one that tries to predict S from that representation. But it's an adversary, so the encoder tries to maximize that loss. And so we'll end up there. These methods are usually variations on that idea. Then we have Turing training, where we take the data as it is for our classifier, but we make specific changes to the classifier so that it results in a fair predictor. That usually involves changing the loss function somehow, but yeah, not always. The gradient projection doesn't really do that. And then finally, we have the post-training, where we consider the situation where a classifier has already been trained on the data, and we're trying to fix that classifier now. So because the data was biased, the classifier is also biased, and now we want to fix this somehow. Basically, you look at what kind of biases does this classifier exhibit, and then try to correct these with some calibration. Okay. Before we get into them, these methods, let's answer the question first. Why can't we just remove the sensitive attribute from the inputs and be done with it? This can, in some cases, work, I guess. But normally, the other features give enough information to reconstruct the sensitive feature somehow. So in a really silly example, there's a data set called the adult data set. And the name is a bit weird. It's just census data from the United States from 1994. So it's just general information about like a sample of the population, like how much do they earn and how much taxes they pay and if they're married and stuff like that. And if you remove the gender attribute from that data, then there's still tons of other things, like if you're a wife or a husband, that are very indicative of the gender. But even if you remove that, there's nearly always going to be some hidden way where the information is still there in features. Like in some countries, men have to do mandatory service in the army. So if that's on the CV, then that's like that give away what the gender is. things like that. Yes, so that's here the justification behind this. Okay, and then we'll talk about the first actual approach to solve this. So this is from a paper by Cameron and Calders. It's from 2008, I think, so or 2010, something like that. So they were pretty early there. And it's a very simple idea, but it works surprisingly well. So this diagram here is supposed to show the distribution of the data. So each color corresponds to one combination of S and Y. And we have binary S and binary Y, so it's 4 combinations in total. And we can see that the yellow one, the S0, Y1 quadrant is the smallest. So those are very underrepresented in the data. Yeah, usually S equals 0 kind of stands for the underprivileged group, or the, underprivileged group, and Y equals 1 is usually the positive outcome. So you can see here that the underprivileged group, S equals 0, has very few positive outcomes, Y equals 1. Whereas S equals 1, Y equals 1, the red part is the largest. So the privileged group has lots of positive outcomes. And so the skew is in that way already there, so that the chance to get a positive outcome is much higher for S equals 1. But also, the whole data contains more points for S equals 1. So it's not just that the outcomes are better, S equals 1 is also just better represented in the data. A wider range of examples are there, so it makes it easier to learn from them because there's like more information there, because there are more samples of it. And this also means that when we train this with expected loss minimizations, which you would normally do, like you take expected loss over some batch or something, then the model will prioritize the samples with S equals 1 because there's just more of them. So to get the expected loss down, you should concentrate on the biggest group. So two problems with this data set here. And to fix all of them, we can just try to make all the quadrants the same size. There are several ways you can do this. One is, of course, you just remove all the data from the bigger quadrant until they're all the same size. Or you try to super sample. Is that the right word? No. Upsample. Okay, I don't know the right word, but oversample. That's right. You oversample the smaller quadrants so that they get bigger. So you just basically duplicate samples from the smaller quadrants so that they get bigger. So that sounds a bit silly. Like, why would it matter? Like, what? We're just duplicating things. Like, how would that have any effect? But it really does. Like, if all the batches are balanced, then the model will just learn much better, and like we'll consider everything more equally and get much better results. So yeah, this is a simple method, but surprisingly useful. There are also other approaches to get all these quadrants all the same. So you could, for example, try to generate more samples of the smaller quadrants with the GAN. For example, you train the GAN to produce new samples, and then you buffer out the smaller quadrants with those newly generated samples until they're all the same size. And then you learn from that. And also kind of works. Good, then we're talking about a pre-processing approach next, where we learn fair representations. This is especially attractive when we are a data vendor. So we have produced, generated or gathered some data through like an expensive survey of lots of people, for example. And now we want to sell this data to other people, but we're worried that there are some biases in the data which we might be blamed for because we produced the data. So what you could do is, instead of selling the raw data, you pre-process it somehow and try to make it fair. So otherwise, if you're just trying to learn a fair classifier, then first producing a fair representation and then learning a classifier on that is a bit like unnecessarily complicated. You just might as well use one of the fair classifier methods that I'll talk about later. But if you're going to reuse the data, then it might make sense to produce a fair representation. There are also other advantages of fair representations. For example, they might be more transparent. There will be a section on that later. Great. So one classic method that I mentioned briefly already is the one where you have an adversary. So I have a mouse. So we start out. Okay. Anyway, we started with the inputs somehow, and we process them through several layers, like it's an autoencoder usually. So here, this way we encode, and then we can also decode it. And there's usually also some reconstruction loss. So when we encode, so we go up here from the input through the layers to the last layer here. And then this layer gives us our representation. And then we use the decoder to go back to the input space. And if we just do this round trip, then the input should not have changed at all. So there's an autoencoder which trained with some reconstruction loss. So the reconstruction should be the same as the input. And then we add this predictor here, which predicts S from this representation. And so it tries to be good at predicting S, but then we have a gradient reversal layer here. So that this part of the network, the encoder, tries to maximize the loss of this here because we invert the gradient here. So the encoder tries for the representation to not be predictive of S, but the predictor here tries to predict S from it. Of course, if you do this, then the reconstruction will not be perfect anymore because presumably you're removing information from it. So the reconstruction must suffer somehow. And usually you also add a predictor for the Y label. if you don't do that, I mean, that's not strictly necessary, but if you don't do that, then usually you would end up with the representation that's pretty useless. Because it, like, all useful information has been removed from it. Like, the encoder is trying to remove S from it, but it just goes too far and removes other stuff from it as well. And so it's not predictive of Y anymore. So we usually have this predictor here, which tries to predict Y from it. And there's no gradient reversal here. So the encoder tries to be good at predicting Y. Yeah, some shortcomings of this is that the representation is just like, it's just a vector of some random real numbers. Like, it's not interpretable at all. So it's very hard to see how the S information was removed. So there have been papers who try to solve that by well, we will see in the section on transparency, this will be discussed. But there are ways to solve this in part. And then the other thing that can happen is that when you have the fair representation, then someone else tries to run a fair classifier on that, like a classifier which enforces fairness during training. So now we have two parts that try to enforce fairness, the pre-training part and the during training part. This has been referred to as a fair pipeline. Interestingly, they don't seem to work. Like something goes broken there. Although maybe this has changed. I mean, this information is maybe from last year or so. So maybe it works now, but I don't think so. It's an interesting issue though. Okay, the variation of fair autoencoder is an extension of the previous idea, where we don't use a normal autoencoder, but a variational autoencoder. And I think there are some other changes as well. So this is the generative model of the situation that we want to treat. So we consider that there's some Z2, which is perfectly fair, essentially, but also doesn't have any information about Y. So this is just noise, to be honest. Or it's just the randomness in your input that's not related to Y or S. Then these two together in our model generate Z1, which has information about Y. So this should be predictive of Y, but still not predictive of S. And then we mix that together with the information of S and get the inputs. So like we treat this as the real model, and then we try to invert this process to go from X to Z1. So, but you see all the elements here from the previous thing where we tried to separate out S, but we still want them to be predictive of Y. So we're interested in this one and not this one. Yeah, so, and because the variational thing, we model Z1 and Z2 as distributions. And what you can also see here is, well, let's see. So what's important is that usually these models all have some kind of reconstruction loss. But we have to be careful that we don't reconstruct just from Z1, so to say. So Z1 is the thing that contains information from Y, but not from S. So that's the thing we want. And if we just blindly try to reconstruct from this to X, and without using the S information, then the reconstruction cannot be perfect because we are missing something, S. So what you should do is you have an encoder from X to Z1, but when you have the decoder, the opposite direction here from there to there, then you need to mix S in there somehow. So when you do the reconstruction from Z1 to X, you need to also include S in this. Otherwise, you cannot do perfect reconstruction of X. So that's an important part. Okay, those were the basic things and the pre-training, I think. How much time do I have still? Okay. So how do we enforce this during training? So we look at the FAR here as an example. So when we don't have if we don't consider fairness, then let's say we have this loss here, just L of theta, where theta is our training parameters, or model parameters. And so in an unconstrained classifier, we just minimize this loss with respect to theta. So we change theta to minimize the loss. So and how can we enforce fairness in this? So essentially, we just add a constraint that the fairness definition that we want to enforce does hold. So what we consider disparate impact, so demographic parity or statistical parity or independence, whatever you want to call it, then we would want this difference to be 0. So this is the probability that for group S equals 1, we do an incorrect prediction minus the probability that for S equals 1, we do an incorrect prediction. And we can, so this, of course, we cannot compute this exactly, but we can estimate it somewhat well. Well, so ideally, you'd estimate this over the whole data set. So at each training step, so first you do your, so if we do gradient descent, you do your model update, you get your new theta, and then you start the next step. And in that step, you first compute the normal loss L, and then also you compute the value of this fairness metric for the whole data set. And you have to do that computation in a differentiable way because you have to do back propagation through that computation. And so then you get an estimate of how far you are off the ideal fairness value where the difference is 0. And so you would, I guess, take an absolute value of that number and then just try to minimize it. So just add it to the loss and then minimize it together. Yeah, I think this is a good place to stop here. So next one is a different topic. I think we're about 90 minutes in, right?
Yeah, so my understanding of the structure is that we're 90 minutes in now. Although there's allocated 30 minutes for a Q&A session, we've got a couple of questions that have come in on Slido. Although I think they've been somewhat answered already, but it'd be good to have a quick chat about them and then have a break because it's a long session, this one, and then reconvene a bit later. So it's 3:30 now and where I am. If we were to reconvene at 4:30.
Oh, so is it first the break and then the question?
No, we'll do the questions now. I'm just saying if in case anybody needs to disappear. So let's go through the questions now, and then we'll sign off and reconvene at 4:30. So 1 hour's time, and obviously 4:30 hour time zone. Not necessarily for all attendees. So there's two questions that I can see so far, and again, if anybody has any more questions, please feel free to submit them. The first question is from somebody called Roman, who says, if we want fairness in regards to race or sex, why not exclude it from the predictors altogether? You touched on this a little already, but we just gave a citation in there of the Padreschi paper from Proceedings on Data Mining, and that was one of the first ones that papers that kind of exposed that this might be a problem. You're perfectly, well, not perfectly, but with a very good accuracy, able to reconstruct a sensitive attribute from other attributes. And the next question might be something quite simple of, okay, well, if I get rid of the ones that correlate almost exactly with the sensitive attribute, why don't if I can measure those, why don't I get rid of those as well? And then maybe get rid of the ones that correlate to a lesser extent. The problem is, where do you draw the line? Because at one point, the only way to really make sure that you're going to do it, remove this information, is by getting rid of all the information either altogether or possibly there's some privacy-based research that might help alleviate some of this. But it's a really tricky problem. Thomas gave the example from the UCI adult data set, the census data, where they've got the category of are you a wife or are you a husband as a relationship status value. And so, yeah, you might say, well, let me remove that. But as he mentioned, that if you, and then you go into the work class category and the different types of jobs that people can have, they're perhaps less correlated, but they are still generally correlated. Where do you draw the line? We've recently been doing a lot of work with images, and simply removing an attribute is not so easy in that setting. So if you take pictures of people's faces, how do you just remove the gender, for example? You can stop it being an exact input, but how do you remove that from someone's features? Thomas, do you have anything to add on that?
Yeah. So the image example, that's a very good one. So say you still want to predict something from the face, like, I don't know, whether someone's smiling, but you don't want to be biased towards a certain gender or something, then yeah, you cannot just remove like 3 pixels somewhere and then the gender will be gone. So you have to do something more clever there to learn a classifier that can still predict the smile, whether someone's smiling, but is not biased by whether by someone's gender.
Next up, we've got some more questions coming in. We've got from Anton, any examples of fairness in AI being a subject of litigation? This is going to test my knowledge now. To be honest, I don't know. This isn't. I'd say that comes from more of the law side that I particularly focus on.
I guess the ProPublica North Point comes closest, although there was no lawsuit.
Yeah, I guess unfortunately we're kind of the wrong people to ask about this, because we focus way too much on the actual the mathsy side of it as opposed to in the real world. We sometimes struggle to tell you what's going on outside of our office door. But if there hasn't been some sort of fairness AI litigation so far, I dare say as it becomes more prevalent, it's something that will be a concern. I know that there's been some a lot of bad press that has been generated, and that usually results in systems being taken down before while they're still in their kind of early stages. But
yeah, there has definitely been bad press.
We say that with some certainty. Next up from Anonymous, how to satisfy the fairness criterion when training the model? Is it enough to modify the loss function, or a kind of constrained optimization is needed? I'll ask you, Thomas. I'll stay quiet and let you answer a bit more.
So yeah, constraint optimization is the one approach that definitely does something. So yeah, is that modifying the loss function? I guess not. So that's just adding a constraint, but you can also do it without a constraint and just modifying the loss function. I don't think we have slides on that, do we?
I'm not sure. I guess one of the things where you modify the loss function directly, or even add some sort of constraint to your optimization, is that all these definitions of fairness are specified with regard to a task. And so you can absolutely do that and take that approach if you want to optimize a specific task to be fairer. The problem is that, and you'll do very well at that one specific task, but if you want your data to be used for either some other task or multiple tasks, then it's not necessarily, well, then you just simply won't be able to do it very well. I guess one of the problems as well is if you're, so for example, with systems like university rankings, for example, where you determine like how good a university is, there's no like one way of measuring how good something is. So you end up having this combination of students per lecturer, hours contacts, satisfaction surveys, and you have a complicated combination of all these things to represent this esoteric thing that you're trying to measure of goodness, and that kind of becomes kind of a proxy label. The combination of these things becomes a proxy for the thing you're ultimately trying to measure. So it can be very easy to optimize for completely the wrong thing. One thing that we don't really talk about very much, but perhaps we should a little more, is that fairness metrics and fairness tools are very useful, but if you flip the if you put a negative sign in the wrong place, you end up creating a model that's very, very biased. And you can have exact opposite effect that you intend to have.
Yes. So going back to the question of whether you can just change the loss function without adding constraint optimization. If I can manage it, I will add slides for that for the second part, and then I'll talk about it. Because I actually worked on a paper that did that, so yeah, good idea to talk about that.
Well, I'll take the first half of the next bit to give you some even more time to put them in.
All right, great.
Cool. Roman says, thank you very much. So I think it's good we answered that question. Next up from Anonymous, is it a good idea to use synthetic data to enforce fairness? So that's kind of a topic that's close to my heart, actually. So let's maybe be a bit clearer around this. So let's say that we have some GAN model that we've trained to produce fair images. So these are images where either it has all the characteristics of a face, but maybe something is a little more androgynous, or it creates data sets that are perfectly balanced in every possible way. And these aren't real faces. So we don't, this has some benefits. Can we use that to enforce fairness? Or we absolutely can use it. And it's something that we've been doing a lot of. The problem is, of course, generating these synthetic data, because that can be tricky. I mean, I'm sure most of you have seen the website thisfacedoesnotexist.com. We're getting very good at generating faces, for example, but there's always kind of they're only ever going to be as good as that model itself. So the model is unlikely to generate samples of things that are too far away from things it's never seen before. It's unlikely to generate somebody who's has green skin, for example, although you might determine that could be a perfectly plausible situation where your machine learning model might, or face recognition model might work. So it can be a good idea to use synthetic data, although I would be very conscious about the model that you're using to generate the synthetic data.
Yeah, so the data, as you said, it can just lack diversity, or diversity in the sense that maybe all the faces look in the same direction and they will never turn or something, because the GAN has never seen that before and then cannot invent it on its own. So synthetic data might be limited in that way.
I guess also one part of the question says about enforcing fairness. Ultimately, the measure of any of this is its effect on the deployment setting. So it might be that you generate on synthetic, you train your model on synthetic data, but if it doesn't perform well in the actual deployment setting, then you've got a problem. That's ultimately the most important part and why we do machine learning in the first place. Cool. Next up from Anonymous. So on the basis of the university application example, I'm worried already. If we have created an algorithm which will be biased towards male applicants and then would force more unqualified women students to apply and not finish, wouldn't afterwards recalculation rebalance itself afterwards and make everything fine? So first off, with the university application example, I certainly don't mean it any more than just an illustration of how different fairness notions can have different impacts. As I mentioned in that example, we don't actually really do any machine learning in there whatsoever. So in some ways, it's kind of a bit silly to use in a machine learning talk, but it's quick enough to describe without getting overly complicated. And you mentioned a point about the system over time. So you've got applications now, and then will that have some knock-on effect at a later time when we recalculate? That notion of time is certainly not expressed in that example. It kind of ties in a lot with the delayed impact stuff that Thomas mentioned. It might be that after a recalculation, it rebalances itself. And in the long term, it might be better in some way. Although without experimentation, I don't know really how we could exactly determine that. Thomas? Don't want to touch this hot potato.
Yeah, nothing to add.
Fair enough. Sorry, it's not a very good answer on that. I think I'd be very conscious. Well, I'm being very conscious that I don't want you to read more into that example than was intended. It's simply just to illustrate that different notions of fairness can have different impact, different results in terms of just putting some numbers on it. And last question, unless any more come in, this will be the last question before we go off to the break. Is there any relation to constraint programming? Good question. My understanding of constraint programming being that you add constraints to your optimization. So when you say optimize subject to these constraints, Thomas, you're more well-read than I am. Have I misunderstood it?
No, I guess that's correct. I haven't seen it used much. Usually people try to express or find some way to make the fairness notion differentiable and then do gradient descent. I don't remember.
Like the Zafar model.
Yeah, even in the Zafar model, it's at first it's formulated as a constraint, but in the end they just add something to the loss, and then it's not constraint based at all, really. Just a gradient descent.
I guess that's one of the tricky things, isn't it? That expressing these problems in terms of constraint can be very difficult to optimize directly.
Yeah.
That's kind of why gradient descent is so popular.
Yeah, but as one of our colleagues said, machine learning people maybe have a bias towards gradient descent and never consider any other methods, even if they might be better. So I would like to see fairness papers that use some other clever method. That would be great.
Well, Anonymous, if we like the way you're thinking, perhaps you should consider applying for one of the 6 PhD positions that we have available. I feel very proud of myself for managing to tie that back to the slide at the start. Yeah, so maybe consider applying and researching that a little more. Do you have anything else you want to add, Thomas? Because we're at the end of the questions now.
No.
Okay, then I shall go make a cup of tea.
Okay, do we just leave this on?
I'm not sure. To be safe, I'm just going to mute and turn my camera off,
right,
and then
yeah.
return at return in 40 minutes. Okay, see you all on the other side.
The recording seems to be live, so.
Yeah. Let's give it a couple more minutes. So I've got 29 past now. We said half past. I think we should wait till at least 31, maybe 32.
Yeah.
Unless there's any objections.
Oliver, did you ask about break? Did you ask about break? Oh yeah, I misunderstood you.
Oh, I was just saying that we asked people to be back at this time now, so 4:30, where we are, and that maybe we should give them 1 or 2 minutes.
Okay, great.
Just before starting.
So I will notify people on the Slack that the lecture has begun, right? Yeah, cool.
Yeah, thank you, Andrea.
Okay, so we're at 32 minutes past now, so I'll start by sharing my screen. Get the right button. Seems to desktop too. Yes. Cool, Thomas, can you see my slides?
Yes, I can see. Do you want to go full screen on that? Press F, maybe it works.
What?
Wow.
It's magic.
Looks great.
Okay, so welcome back, everyone. Those of you who have come back, we have absolutely no feedback from the end as to how many people are either watching or not watching. So we're just going to assume that there's some people who have come back for the second part. You enjoyed the first part so much, you thought, I know, I shall waste my Friday evening watching two people talk about fairness in machine learning. So thank you to those who are back. So I want to start off by quickly talking about the structure of this second part, because it'll be slightly different from the first, and then also do a couple of housekeeping things. So let's start off with those. First is that we are have all these slides available online. They're all at our website, which is predictive-analytics-lab.com/presentations. You'll see a few variations of this talk that we've given previously, and you want to select the one for this summer school if you're following along by yourself, or if you want to recap. Alternatively, you can just watch along. watch along with these slides. So the structure is going to be, oh, by the way, if you are following along, we're at /79 at the end. So although we're slide 106 here, if you want to jump straight to it, the HTML, the URL is /79. So this, as I said, the structure of this part of the talk is going to be slightly different than previously. You'll notice that according to the slides, we're roughly 2/3 of the way through. That's by design. And the structure will be roughly like this. I will speak for a while about transparency and fairness and the project we've been doing there. Then shortly afterwards, Thomas will be speaking about causality with regard to fairness. And then after then, we're going to have an introduction to the lab session that we've got lined up. We put a lab session at the end of our talk as kind of a really good kind of catch-all time. So if we're slightly over or slightly under, it doesn't matter too much because we've got the lab session that will fill the rest of the time. We'll give you an introduction to that, all the things that you need to know to be able to make that work. And then we'll have a Q&A session before going on to before starting the lab session. So talk, introduction to the lab, then Q&A, and then the lab session. And if you want to communicate with us further, then you can do so via Slack. I've sent a message to the channel with our details in. Also, there's a link to the repository for EthicML, which forms the core of the lab session. Please feel free to reach out to us via GitHub. That is probably our preferred method of communication. It's both of us are probably coders first, so it's the one we feel very comfortable. So right, let me begin. So up to now we've spoken about different notions, why we should care about fairness, different notions of fairness, and then practically how do we how we might go about doing some enforcement of fairness. Now we're going to move to slightly more application side and practical side. And so I want to speak about a couple of recent projects that we've worked on regarding transparency and fairness, because I feel like it's a really important area that is sometimes overlooked and is something that we're very proactive on. And then Thomas will take over to speak about fairness and causality. So Thomas gave a very good introduction to this idea of pre-processing fairness or affecting fairness at this kind of first step. So adjusting our data so that it matches, it becomes fairer for some downstream task. Usually typical approaches for this involve some sort of gradient reversal layer from domain adaptation literature. It's a very successful technique that's used in a number of places. I've taken this screenshot from the Madras et al. Paper, which is cited at the bottom of the screen, Learning Adversarially Fair and Transferable Representations, because I think like it gives a good overview. So we have some input X. I can move my mouse right to see that. We go through some encoder to some representation, such that we can then go back from the latent embedding with the decoder back to the input space. But we don't only just take the input space, we often sometimes take the sensitive attributes as well. So the two together help decode the original input. This helps us remove information from Z about S, and we do that we're using an adversary. And then from the latent space, Z, we go to make a prediction. Sometimes in terms of if you want more transferable representations, you can basically remove this classifier head, because whilst it helps get a representation good for a specific task, if you're looking for a more general approach, then you can simply remove it. There'll usually be some payoff again in terms of accuracy, which is a common theme of the fairness accuracy trade-off. So we've been looking at this, and though we're very we're behind this approach, we think it's very good. There are some problems or areas that could be improved upon with this whole general setup. And the biggest problem we have is around this latent representation Z. So by latent representation, we just mostly mean that Z is in some space that we don't necessarily fully understand. It's the input space we know about. We know when we take an image, we understand pixel space. It's something that we can interpret visually, particularly when we take into account the space aspect between pixels. Just so basically saying that we can understand groups of them together. Also, if we were getting census information, for example, we can usually understand what each column of the census answers refers to. So in the age column, providing they've returned some value between, say, 18 and 110, that would make sense that it's the age that the people have given as input. But when we transfer this through some network to an encoding of some Z, one feature there could be a combination of almost all the features, and we have no way of really understanding what the number 4 on node 3 of our representation means. It just doesn't mean anything to us, although practically it's very useful. So what we'd like is to really be able to understand how the model made it so that it became fairer. So what is the encoder doing to produce this fair Z that makes it fair? Otherwise, it could be doing things that we don't intend, or it could be giving us some insight into what needs to be done to make something fairer. So this is so I'm going to give an overview of a paper from CVPR Computer Vision and Pattern Recognition Conference from last year, and as it gives a really good sort of introduction to this kind of setup, and then we'll go further, coinciding with works that builds upon it. So we have some fair representation T of X, which has the sensitive attribute removed but remains in the space of X. So what does that really mean? It means that we've got some image, for example, of a face, and we want to be fair, I guess, with regard to some specific sensitive attribute. Let's say it's male, female. So if you took a picture of my face, the parts of the image related to my face and my gender, if they were removed, what would be left? So for example, my beard, you might expect, would be removed. You might expect some change around my hair length, for example, or features certainly that correlate in the training data with some sensitive attribute. So there's kind of a main disentangling assumption here that is, if anything, too simple, but is, for a starting place, is a good place to start, which is, let's assume that we can decompose an image into the fair part, and then there's like an unfair part that goes on top. When we say unfair, I don't really mean unfair, I just mean all the parts that are related to the sensitive attribute. So for example, in the case of my face, if we remove my beard, the spurious part according to these slides would just basically be a cutout of my beard, and TX is me without a beard, and then add them two together as though it's an identikit kind of setup, and then you have the original image. So it's a very simple deconstruction, and if anything, too simplistic, but again, it's just a starting point of trying to make it so we can understand what's going on. So we use the term spurious here, so that spurious being dependent on the sensitive attribute, and non-spurious, which is independent of the sensitive attribute. And this is a setup of the model. So let's try and disentangle, to use the word again, this a bit. So we've got some input space. We're going to go through some model T that produces some fair representation or some fair version of the input image. So from our input, we're going to have some reconstruction loss between these two images, so that try and make sure that they're in the same input space, that make sure that this T of X is not some crazily wild and different image. We then have some measure of how much spurious information or how much sensitive information is in each section, and then we have a prediction loss as well. So we want to make sure that this is still suitable for achieving some task. So in many ways, it's kind of a natural successor to this kind of setup. Yeah, the biggest difference here is we're saying that let's make this Z be constrained to be in the same space as X. So if we consider pixel space, let's make sure our Z is also in RGB pixel space. So when we first spoke about this, the obvious question was, well, can't we do this with a GAN? And unfortunately, not exactly. GANs do really, really well when we've got examples from one domain and then the domain that we want to map to. The problem is that we want to kind of map to a domain that doesn't exactly exist. So really we want to move someone's face to a space that's neither male nor female, or neither one race nor some other race, or any other attribute that could be considered sensitive. So we can't use a GAN to directly map. Normally I gloss over this, which is kind of the optimization problem that we had, but given the summer school, we should probably delve into this a little bit more. And the bit I particularly want to talk about is this HSIC part, because this is kind of where the magic is happening. So if we look back previously to here, in previous work, we see that the adversary works best, well, not works best, but is often used with a gradient reversal layer that Thomas spoke about in some detail. You can enforce fairness with other methods. In the variational fair autoencoder that he spoke about, they actually use something called MMD, or maximum mean discrepancy, to compare distributions in the Z space and the latent space. And we're going to use a kind of variation on that called the Hilbert-Schmidt independence criterion, which is referred to as HSIC because the other one's a mouthful. And HSIC is a statistical measure of independence, and really one thing that we're measuring is the independence between the joint distribution and the product of the marginals of two distributions. So in this case, one distribution is the sensitive attribute, and the other is our spurious or non-spurious image. So the way that HSIC works is it works out the MMD between the product of the between the joint distribution and the product of the marginals, and then you end up with your HSIC. This has a kind of benefit, because if we were just doing MMD between two distributions, as I mentioned earlier, when you start looking at a number of sensitive attributes, your number of equalities grows combinatorially, so it gets quite large quite quickly. Whereas with HSIC, we're directly comparing the representation, the T of X, or I kind of want to say Z, but that's not fitting in with the previous language. But our T of X, our fair representation, pair that directly with the sensitive attribute. So the number of sensitive attributes can increase, but we still only have one measure to look at, which is very useful. So we've done this, and we've taken a look and see how well it does. Thomas previously mentioned the UCI adult data sets or the adult income data sets, and he gave a very good description of it. But just as a recap, it's a data set, census data from the 90s in the US, and it's frequently used in fairness research. And part of the reason for that is it's a difficult task. Certainly predicting over 88%, 89% is very, very tricky for the task. So getting a perfect predictor is very difficult. It also has the benefit of it's got at least one attribute that we can consider sensitive. So we can perform either measures regarding gender as a binary sensitive attribute, which it collects, or there's race, which is more than binary. I think they list 4 races. It has over 45,000 data points. Each one's got 14 features, such as relationships, status, gender, and occupation. And usually we one-hot code some of these, so it becomes more like 60-odd features. And we use gender as a binary sensitive attribute because in these slides we're remaining talking about binary to avoid all our equations going off into the next screen. And so the task in this is just to predict, or to predict whether a person is a high earner. Do they earn over $50,000 per year, or do they not? So one of the things that we can do, or the benefits of making the latent representation space be in the same space as the input, is then we can determine what has changed. So when we did this, we looked at those samples that had changed in their prediction, so compared the original to this fair version and see what changed. And the big thing that happened was regarding the wife and husband. So the relationship status has these values: husband, not in family, other, wife. And obviously this is almost a direct proxy for gender. And without being instructed, it managed to find this pattern, and it simply removed the values of those with the wife and put them to the husband category. You might say, why that way around and not another, and not the other way around? In this data, there are about two-thirds of the data set are male, whereas 1/3 are female. So it simply moved them to the majority class. But it provides useful feedback, because although we know that this is a category that is potentially related to gender, there are other categories as well where perhaps this wasn't so obvious to us, but it's providing feedback. I won't bore you with looking at results. Please feel free to take a look at those in your own time. The gist of this being, though, that you can get a fair representation that you can understand without a massive, or any really, loss in performance, which is good. You kind of get transparency for free. So tabular data sets are great and all, but they're not that exciting. So we thought, let's go one step further and look at the Celeb A data sets, because images are way more interesting. So in this, we use gender as the binary sensitive attribute, and this is actually work from a year or 18 months ago. We considered that the attribute memorability was the classification task. I think when we do this work now, we tend to use something a bit more explicit, such as smiling or not smiling, but we use memorability in this. And if we take our model and we try it and just assume it's additive decomposition, we kind of end up with these weird looking pictures, which are a bit strange. At the bottom, it almost looks like they're black squares, but if you were that so interested, you could really zoom in and see almost green splodges on them. These correlate to the images above. So if you add these two together, you'll end up with exactly the input image. You notice the areas that have been affected though are the mouth and the eyes. It kind of tells us, if anything, there's kind of a bit of an attribution map of this is where the information regarding the stuff regarding gender is, or certainly appears to be in this model. So let's not hide away from the fact that spurious and non-spurious visualizations are just not exciting here. These aren't particularly nice to look at. They don't really feel as though they're giving us that much information. But if we compare this to a latent space, we're certainly heading in the right direction, or certainly heading towards a more transparent and interpretable representation. With some numbers on the screen, I'm just trying to work out if they are mentioned again. They're not exactly, but they're really useful because this is part of the reason why we then built upon this work. So they're useful for background. Here we have something called the colored MNIST problem, which is kind of a useful toy data set in terms of fairness in images. And on the left-hand side are samples from the training data set, and on the right-hand side are samples from the deployment setting. So this is where we're going to use our model in real life. On the left-hand side, you'll notice that all the 9s are yellow, and then you might notice that all the 2s are pink, and then all the 8s are red. And pretty soon you've taken a look and you've realized that actually there's a one-to-one mapping between color and class. If you were training a model on this, and you had, well, if you train a model on this, usually what will happen is that your model learns to pick up color as a direct proxy for the digit class. The reason for this is it's a lot easier. You can look at one pixel and aim for one pixel pretty much in the middle or just to the side of the middle, and you'll be able to determine from that pixel color what the class should be. The problem is if your model falls into this trap, when it gets to the deployment setting, it will get completely wrong answers. On the right hand side, you'll see it's no longer the case that all 9s are yellow or that all 2s are pink. So we've got a real problem here that our training setting doesn't match our deployment setting. This is for those who've looked at domain adaptation before will certainly be aware of this is something similar. And this is something that we kind of want to be careful of. This is kind of referred to as residual unfairness. It's not exactly the same, but it's this idea ultimately that the training data isn't representative of our test set or our deployment setting. So if we learn patterns in the training set that are going to, so if we learn patterns in the training set, we might end up propagating something that is just simply not really true, but we're going to propagate it and it's going to get on further. So what we want to do is try and deal with this problem a bit. And to do this, we can build on some of the work that we've done previously and look at it kind of from a generative modeling approach. I'm going to switch on to the next slide because the first, we're going to do it in kind of two ways. One is a bit more normal, and the second one we're going to use an invertible network to do kind of the same thing. So let's look at what's going on here. We've got some input. So this should be a very similar kind of setup to before, but with a completely different looking image, just to make things confusing. So we go from the input to some encoder to some latent representation Z. Now this Z has should be invariant to S. So here we go, ZD to S, and then the Z and S together go through the decoder to reconstruct our X, and we make sure there's a reconstruction loss between the two. So if you look at that compared to say this one, the two are pretty much identical. The only thing that's different is that we lose this classifier head. And why do we do this? this is because we want to make sure that this word here is transferable. So we're not building too much of the properties for classification into the embedding. All we want to do is just remove the parts that relate to the sensitive attribute. So we'll do this during training time, and then at deployment time, we'll feed our image through the encoder to get our representation. And then instead of feeding through the sensitive attributes into the decoder, we're going to fill out a vector of all zeros or some mean value, something that is neither, doesn't mean 1 for male or -1 for female or vice versa. It's just something in the middle of them to take us to something that should be neither. Then we decode, feed those through the decoder to get our fair version of X, and then we can use a classifier downstream on this task. Before we look at the results, one thing that you kind of notice is that because we've removed the classifier head from this whole setup, which a lot of models have, in fact, even which this model has as well, has a prediction loss on it. Because we do that, we don't actually need the class label during training. We only need to know the sensitive attribute. So providing that our training data is, so we place less constraint then on our training data. It doesn't have to be labeled. And because it doesn't have to be labeled, that leaves a massive constraint. It means it's a lot easier to get hold of unlabeled data than it is labeled data. And when we only need the sensitive attribute that is often collected anyway, it means that we can pre-train our model, well, our training, during the training step. We don't necessarily need to do it on the labeled training data. We can reserve that for the classifier training. Instead, we can use this on some unsupervised training set that more closely resembles the deployment setting. So in the LvDS case, we could pre-train on the deployment setting, which would give us way more information about the relationship between shape and digit, and gives us way more information about just the shape, and then we can learn to disentangle that more from the relationship between the color. So we did this, and we ran this on the Celeb A data set, and you'll notice that one of the problems is that these images get really quite blurry. So when we're trying to draw conclusions about what a model is changing about our representation, it becomes very tricky to determine, is that due to the blurriness generally of our model, or is this something more profound that's happening? So if you look at some of the, well, you can look at any of them, but trying to determine whether that is due to just the general blurriness or something more profound is a very tricky challenge. So how about if we do this, but instead of using just a general variational autoencoder or autoencoder setting, how about if we make use of invertible neural networks, which are a class of network where no information is lost. So data is transformed in some way, but it's exactly bijective. One input in, so if you map from X to Z, one input in X matches exactly to one input in Z and vice versa. There can't be two inputs that match to the same latent space. And similarly from the latent space, it can only map to one possible input. The only thing that happens is the data gets shifted around a little bit more, which is kind of useful. We can we then take this idea of maybe we can learn to, when we're shifting, we can sort of partition to one side the bits of the data related to the sensitive attribute. So this image looks different to the previous one, but it's actually very, very similar. It's just because of we make use of the invertible network, we can remove another loss. We can remove the reconstruction loss, which anyone who has trained models previously knows less losses the better, or fewer losses the better. So if we go from here, during training, we go from X, we go through our invertible network to some representation Z. Previously, we just went to ZD, and we relied on our encoder to throw away parts of the representation that were related to the sensitive attribute, which was ZB. But because it's an invertible network and we can't lose any information, we have to retain it. But what we're doing here is we're just partitioning it. So we're saying all the bits, all say the last three, say, variables of the Z embedding, they are all to do with the sensitive attribute. We then we enforce this by using an adversary to go from the ZD, the bit that we said shouldn't have anything to do with the sensitive attribute, and feed that through an adversary to predict S. The red with a line denotes it, red with a line through it is denoting the gradient reversal layer from Gallin, which we've spoken about previously, and is littered throughout fairness literature. So that's during training time, and then to make sure that if we wanted to test this at any point, we could take our embedding here and feed it back through the INN and get our X, but because of the properties of the network, we know we don't need to do this. Then at training time, then at testing time rather, deployment time, when we come to use this in the real world, we go from X to our representation Z, and we take out the bit that's related to the sensitive attribute ZB. We just essentially pop it off, and then on the end pop a vector of push a vector of zeros. So this is very similar to what's happening over here. Apart from here, we explicitly add a vector of zeros rather than the input, rather than sensitive attribute S. Whereas here, we just, instead of having the attribute S, we have the bits that are correlated with S. And we push that onto our representation. We can push this through reverse ways through the invertible network. And we end up at XD, meaning we're back in the input space, but we have a kind of a fair representation in the input space. And we can then go on to use a classifier on this downstream task. So these are some images that line up from using that model. And one of the things you'll notice, I didn't explain this earlier, so let me do it now because the same holds true on this. It's the same layout. On the left-hand side is the input image. And then on the middle one, we have the XD. This is the fair part with a vector of zeros instead of a sensitive attribute. And then on the right-hand side, we have these kind of weird-looking general faces, which look even weirder and more scary here. These are, if you, instead of doing it this way around, where you feed through the ZD vector, if you instead just fed through the ZB and replaced ZD with a vector of zeros, so you kind of flip it around, what would you have? So you should end up with the middle is the kind of fair version of the image, and on the right-hand side is kind of the unfair bits, or the bits of the image that are most related with gender, but they're mapped onto kind of a mean average face. And one of the things that you'll notice is the images are certainly sharper, and because of that we can feel a bit more confident in drawing some conclusions. So starting off in the top left, this person here is wearing sunglasses. For a start, we'll notice that our model doesn't really look very good. with sunglasses. It's something that produces quite a weird looking image. So that might be something that we feed back and say, actually, if you're going to use our model on somebody wearing sunglasses, the results might be a little askew. There are other cases where it does quite a good job of changing the, making quite stark changes. However, one thing that generally seems to happen throughout our model is that skin tone is somewhat changed. Generally, it seems that people become either lighter skinned, or there are a few occasions where the contrast is kind of increased. This is probably not what we intended to happen. We're trying to be fair with regard to a sensitive attribute, and we didn't expect that skin tone might be changed in some way. So being able to see that this is happening and feed it back to people who are either using this model or have created this model, and say, hey, this is something that we didn't necessarily expect, is very is a very useful tool to be able to have. We kind of expand this slightly further, and I won't go into this project too much, other than to say that instead of switching to a mean vector of zeros, what if we just used samples, labels, sensitive labels that have already existed. So instead of going to some mean place, let's try and make a male and a female version of somebody, and try and balance that way. This would tie together some of the work that Thomas mentioned about the reweighing from Cameron and Caldas, tied together with a generative model, to create a kind of contrastive data set. So for every person, you end up with their a likely version of them, but with another sensitive attribute. I won't go into that too much. I'm happy to speak about that at a later date if anybody would like. Next up, we have our slides on causality, where Thomas will be speaking in some greater detail about causal models. Thomas, either?
I'm here.
Fantastic. I'm going to stop sharing my screen now,
Please.
and then you'll be able to take over.
Okay. I'll try also go full screen. Did it work?
It did. It worked splendiferously.
Great. Yeah, so I won't be talking about causality just yet because I just added some slides here. So I'm going to talk a bit about what I mentioned in the Q&A, the fairness without the constraint-based optimization. So most fairness methods, even though most fairness methods are actually just fair representation methods with an adversarial layer, but if you only look at the ones that are for during training, so in process fairness methods, then most of them are based on constraints. So we try to optimize the loss, but also have the constraint that our predictions should be fair in some sense. And when you have such a constraint optimization problem, then either you're actually going to do constraint optimization, which usually doesn't happen, but it could be possible, or you're using Lagrange multipliers. And let me briefly remind everyone how that roughly works. So we have a constraint optimization problem where we try to minimize some loss f with respect to the parameters theta, and such that some function of theta is equal to 0. So maybe you don't want the function to be equal to 0, but you can always reformulate it such that something's equal to 0. Just subtract things from the one side so that you have 0 on one side, and that's your constraint. So this is fully general. Any constraint can be formulated like this. And then you introduce a lambda parameter, which is the Lagrange multiplier, and just multiply your constraint by that and add it to your loss function. And in theory, for the Lagrange multiplier to correctly work, you would have to determine the value of lambda, some process, but in practice, people just set it to some value and they try out like some values and see which one seems to work. And that way you have transformed the constraint optimization problem into just a normal problem with a normal optimization problem with an additional parameter lambda. Okay, so that works reasonably well, but some things are not so nice about that. For one, the lambda has no meaning. If I tell you the best value was 0.1, then it doesn't tell you anything. And beforehand, you also don't really know what value it should have. And second, it doesn't give you feedback on how well the constraint is fulfilled. So we just add this to the loss. Well, okay, you can log the loss separately, but it's often hard to tell how lambda influences this. And there's an alternative way that I worked on, actually, where you introduce some pseudo labels, y bar, and then these become our prediction targets. And we make sure somehow that these pseudo labels are fair. So this is fairness with respect to demographic parity. It's always the easiest. You can also adapt this to other fairness notions. So in demographic parity, we want the predictions to be independent of the sense of attribute. And that's what we enforce for the pseudo labels here. So the pseudo labels are independent of S. And then if we train a classifier with that, then we hope that the classifier's predictions are also independent of S. But we don't have the Y label, like we don't know what they are, but we can implicitly use them. So we never calculate them explicitly, but we use this expansion of the probability. So in this formula, you see here on the left, it's just a likelihood. So it tells you, given your current model and some input X and some sensitive attribute S, how likely is it that Y is equal to 1, like according to your model? That's the likelihood. And with the pseudo labels, we compute this indirectly. So first, we compute the likelihood with respect to the pseudo label. So this will be the normal likelihood function of your method. So for logistic regression, it's the sigmoid function. And then we have here this term that shifts these probabilities. So it tells you, given some pseudo-label, how likely is it, and some sensitive attribute, how likely is it that the observed label is 1? So this is also kind of a likelihood for the label. It establishes a connection between these two. So yeah, I won't go into more detail on this. I mean, maybe it's not completely clear how this works, but this is the rough idea. So we have some pseudo labels and use them as new targets, and we implicitly define them via this probability here. And to get this probability, you can you look at the fairness constraint you want to satisfy. So for demographic parity, it's this one. So this will lead to that Y bar is independent of S. So if you enforce this, then through some probability calculations, you can calculate this value, and this will tell you what value to put here. And then it all works out that Y bar is a target that's independent of S. And then you can just train your classifier normally with this likelihood here. Yeah, for more details, you can look at the paper. It's published this year. Okay, then another brief mention before I go into causality. So the usual way we measure how well we did on the fairness is we compute so for demographic parity, we compute the acceptance probability. So P, the probability that the prediction Y hat is 1 given the input, given the sensitive attribute, sorry. So we look at what's the positive rate for a group S equals 0, what's the positive rate for a group S equals 1, and then we take either the difference, which we hope is 0, or we take the ratio, which we hope is 1. So these are two measures of measuring how close we are to fulfilling demographic parity. But ratios and differences only work for two values, of course. So if we have more than that, so have multinomial S or multinomial Y, then this doesn't work. So one thing you can do is kind of compute all the possible ratios and then take the average of them. But what's much nicer is to use the Renyi correlation, or the full name is Hirschfeld-Gabelein-Renyi maximum correlation coefficients, short HGR. And that's a really nice measure for telling you how dependent two variables are. So you know that normal correlation only finds linear relationships because it's computed for matrices and stuff. There's actually one shortcoming of the Zafar method. They use, if I remember correctly, they use correlation to estimate the dependence of S and Y, S in the prediction. But it's not a perfect measure because it only finds linear relationships. But HCR finds any kind of relationships. And so it's basically just like mutual information. So if, in fact, if HCR is 0, then the mutual information between Y and S is also 0. So if Y and S are independent, then you know the mutual information is 0 and HDR is also 0. But the shortcoming of mutual information is that it doesn't have an upper value. It can go as high as it wants. But HDR has an upper value, it's 1. So if HDR between Y and S is 1, then they're maximally dependent. So there's a deterministic function between them. You can get one from the other. Yes, so that's a very nice measure. And it also works for continuous Y and S, but then you cannot compute it precisely anymore. Yeah, then you have to estimate it. Okay, let's start with the causality, first topic of our presentation. So, what we have looked so far is kind of only looking at correlations between S and the prediction, sense of attribute and prediction. Like even this here, like it's not a linear correlation, but it's still kind of a correlation. We just look at, yeah, like mutual information or something. But even if we consider mutual information between the sense of attribute and the prediction, it's still not really the right thing, maybe. Maybe we should look at the causal path to really determine what's going on. So what do we mean by that? Let's consider an example. It's a classic example found in lots of textbooks, I think. There was a case where the Berkeley colleges were accused of having discrimination in their admissions. So male applicants were accepted, which had much higher rates. And so it was very obvious if you looked at the data, like males were accepted much more often. And so it seemed like there was blatant discrimination. But that's not necessarily the case, because when you look more closely, you saw that the reason was probably that women were applying to more competitive departments where it's harder to get in than men. And so women were accepted less often because they were applying to the more popular things. So for example, medicine and law are very competitive fields. It's hard to get in, but computer science is much less competitive, maybe because it's boring. I don't think so. Maybe people think that way. So, what does that mean? So yeah, so it seemed like the reason wasn't actually the gender of the applicants, but which department they were applying to. So we can draw a nice causal graph of this. Unfortunately, the sense of attribute is called A here. We call it S everywhere else. I'm very sorry about that. I wanted to reuse their graph and they used A. A is also often used in the literature. So we have R is the decision, whether someone is admitted. A is their gender or any sense or attribute. And X is the department choice. And then we draw causal paths here. The gender seems to influence the department choice, like women preferring psychology or something to math, I don't know. And the department choice affects the admission decision. But there might also be a path from the gender to admission decision. And this is the path we don't want. So I circled it red here. But the other path seems fine. I mean, you can maybe complain or worry about the fact that women don't want to do computer science, but this is not the admissions department's problem, probably, but some other reason. So this path seems more or less fine, but this is problematic. And what you should try to find out is whether this path is used in the decision making. Yeah, so what causality enables us here is to understand the issue much more deeply. So we can really see why the data is like it is. Like in this case, we found out it's the department choice. That's very nice. And in order to turn this into like a fairness method to use, the idea would be to only allow, like if you're making an admissions algorithm, then the algorithm must not use the gender directly. It may only use it via legitimate causal paths. And for that, we need a causal model. And here we hit the first big problem of this idea. Causal models cannot be inferred from observational data. So, so what I mean by that is, in this graph, we can compute all the conditional probabilities here, like what's given a certain gender, what's the department choice. But what we cannot get just from observational data is the direction of the arrow here. So, of course, our common sense tells us that department choice does not retroactively determine your gender. Like from causal information alone, we know that. From temporal, like time information alone, we know that gender came before department choice. So the arrow must be in this direction. So in this case, it's fine, but in general, we cannot tell the direction of the arrows from observational data, and thus it's a big problem to get these models to use them and to use them. The way you get causal models is by doing experiments. Like if you want to know whether cancer causes smoking, you have to force some people to smoke and observe whether they get cancer. That's like the correct way to do it, I guess. But that's often not ethical. Like, you cannot just force people to smoke. So in current work, people just guess the causal structure from common sense. There are other ideas to do this, which actually some of my colleagues are working on, but don't know where they work. Yeah, so if we then have the causal model, then we have to decide which paths are fine. So in this example, someone determined that, so we were predicting Y, and someone determined that using L is fine as a feature. I don't know what they stand for here, but so even if the sensor attribute goes through L, you can still consider it to be okay, but going the direct way is certainly not fine. That's like never fine. And going via M in this example here is also not considered fine. So M might be like marital status, for example, then actually puts with 11. So if A is gender and M is husband or wife, then of course that's basically just A, so we don't consider this a valid feature. But L might be like department choice, something like that, which would actually be fine. But in this case, M affects L, and thus this is also problematic. So you see, it's not easy to disentangle all this and decide like which features we're allowed to use. But there is theory for this. The theory of causal models is pretty well developed. Maybe you even heard a lecture about it. So, and if you have a structural causal model like this here, where it says exactly how each of the variables depends on all the other variables, then it's very possible to just compute a fair version of this that doesn't take into account A. So the advantage of the whole procedure is that we can very precisely control which information we want to consider and which we don't. The problem is that we require a structural causal model, which we usually don't have. And it's actually also a lot of work to go through all the features and decide whether it's admissible or not. Like for 5 features, this is still fine, of course, but during computer vision, that will not only be 5 features. So, and in addition to path-specific fairness, there's also counterfactual fairness, which is very similar, actually. But not as finely controllable, I guess. It's also based on structural causal models. And we're asking a counterfactual question here. So if you have never heard the word counterfactual before, it's a word from philosophy. It means something that has not happened or is not the case. So not fact. And counterfactual questions are basically about possible worlds that are not our world, but which could happen. So one classic example here is, if Oswald had not shot Kennedy, no one else would have. This is a very common type of statement that people make. You specify some condition that in fact wasn't true. So this is completely counterfactual because Oswald did in fact shoot Kennedy. Well, except if you believe in some conspiracies, I guess. But so, as you normally wouldn't notice anything weird about this sentence, but it is actually kind of weird because we're talking about something that didn't happen. So how can you make statements about this world that didn't actually happen? But humans seem to be able to do these kind of statements. So we can try to formalize this thing and try to develop a theory for it. And this is what people did. And which leads to counterfactual fairness. So this again was a structural equation one. Okay, I have to go. Use this figure to explain. So the gray nodes in this are observed, and the white nodes are unobserved. So this is a law school entrance exam data set. Oh yeah, so FYA is the success in law school. So it's the average of the first year grades. And the GPA score is, I'm not American, I think you get that from college. And then you also do a law school entry exam. So what we're trying to do here is predict the success in law school from the GPA and the LSAT. And we also have race and gender information. And so first of all, we have to decide the direction of these arrows. The data cannot tell us the direction, but it's, again, pretty obvious that your GPA doesn't cause your race, so error is probably in that direction. But this is unobserved, and we don't know which one's true. So in this paper, they just tried out both versions. So in this model of the world, all three of these things are determined by an underlying variable called knowledge. So there's some knowledge thing in your head, and this one determines all three of these, which makes some sense. But in the alternative model here, there are actually three different things, like, I guess, ability to do good GPAs, an ability to be good on the LSAT, and an ability to be good in law school. These are all strongly correlated with each other, but there's still three different things. So this model on the right is more expressive. It allows more variation. So more complicated scenarios. So anyway, so the white ones are unobserved. So that's just what I want to point out. So, and in this case here, we consider U to be the set of all unobserved background variables. So in this case, it would just be the one here, the knowledge. In this case, it would be all three of these. So, and to do now the counterfactual thing, we set, we keep all the unobserved background variables, but we change one node. And so we change sex or race in this case. And so we look at the counterfactual world where everything is the same about you, except you have a different gender, for example. And we check that in that counterfactual world and in the actual world, the probability that you get accepted is the same. So that makes sure that the gender did not affect the outcome of this situation. Okay. So that's the idea. And in practice, this has similar consequences as the path-specific fairness that I talked about before, namely that you may not use any information that you may not use S, of course, for your prediction, and you may not use any descendants of S either. So doesn't make any sense to this. Descendants are things that S points to. Why is counterfactual fair if it does not causally depend on S or any descendants of S? I'm not completely sure what the practical effect would be in this case. Sorry. should have prepared that better. But yeah, this is again, yeah, okay. Yeah, you still can use, right, of course, you only make use of knowledge here. Yes, because these are all biased. So you can only make use of knowledge to make the prediction here. Knowledge you have to infer from these, of course, but yeah, you may not use these directly. Yeah, same here. Okay, sorry. Good. So that's great definition, but the problem is, of course, getting the structural causal model, and which we cannot get from observational data because there's no unique solution. Like several arrow directions are compatible with the data, but the arrow direction is very crucial then because it tells you which features you're allowed to use. Right, I talked about this. Okay, so my summary of this is that causal models are pretty cool, but they're difficult to get. And this was only tabular data. Like for image data, I don't even know how we would do. Good. This is summary of all we presented. Oliver, do you want to go through this again or something?
No, I thought I'd pop back up, seeing as though we're towards the end of these slides, and apologize for turning my camera on and shaking my head. As a computer scientist, I will not stand for any disparaging remarks whatsoever about a wonderful topic.
Yes. Yeah, these are our take-home messages. This is just a repeat slide from the beginning. Fairness is domain specific. There are multiple definitions that you can use. If you predict anything that will affect people, you should consider it. Accuracy is nice, but not the only metric you should look at. And fairness is active and exciting. And again, the reminder that you have.
Cool. So what I wanted to do is remind everyone that we're going to do a Q&A. So we quite enjoyed it last time because whilst we've seen our slides lots and lots of times, we haven't seen any of your questions before, so it's far more exciting to us to answer the questions. As we've, in terms of time allotted for this session, we allotted 90 minutes for the second part of the talk, which would take us through to 6, so about 13 minutes away. So that's why we built a buffer of our lab exercise for that. So what my plan was to give you a quick introduction to the lab exercise, just to show you it broadly. And whilst I'm doing that, if you have any questions that you want to ask, please use Slido. I can see a couple coming in. After I've given a brief example or brief overview of the lab exercise, we'll pause that, come back, answer some questions, and then we'll leave you to continue the lab exercise. And then if you enjoy it and you want to ask the questions, or you do something on there that you enjoy, please, or that you're proud of, please do get in contact with us via GitHub, which there's a link as part of the exercise. It's raised an issue, and we're very happy to talk via that mechanism. So let me share my, well, let me first start open a browser, and then I shall share my screen. Cool. Hopefully you can see that. Oh, no. There we go. There we go. Hopefully you can see that. So if you're following along, if you just remove the part specific to this summer school, you'll see that our main presentations area here we've got an exercise which should launch a Google Colab notebook. I ran this morning, so I feel fairly confident that it runs, but there is one slight little trick to it because Colab's not recently updated in terms of everything. We have to do one small slight trick to make Pill work with it, which is part of our library. So the URL for this notebook, if you don't want to follow along using the predictiveanalyticslab.com/presentations link, you can go directly to tinyurl.com/ethicml. And then before we start, we just have to update a couple of Colab's dependencies, which doesn't take that long. And then once you do that, you have to restart your environment, but then you don't have to rerun this again. Cool. So while that's going on, there we go, that's happened. And then you have to hit restart runtime. Cool. So this is a brief overview, and here you'll see a link to ethicml. This is a link to our GitHub page for this project, our repository. If you want to get in touch, please use issues. Whilst the issue sounds like a problem, we very much use it as a way of communicating not only with each other, but generally amongst our group as well. And it should give you a little overview of what's going on. So first we can install from pip, and you get lots of information about the type of data that you have available to work on and different ways of analyzing the data. So you should be able to click through all of this. Once this is done, I'll do that just to demonstrate that this definitely runs. So we can load in some data sets, and we can, there we go, we can take a look. So we can see it's running. So that's there for you guys to look at, to have a play around with, kind of get a bit of a feel, and hopefully decide that ethicml is kind of a cool library. Or alternatively, please feel free to feel like it's a terrible library and think, I know what I could do to make this better, and feel free to contribute. We'd very happily work with any of you on this project. So let's head back to the, let me stop sharing my screen now, and then let's head back to the Q&A, and then make sure that, I would share my screen if I could find the thing, there we go. Let's head back to the Q&A questions, then we'll leave you to enjoy your Friday evening, either with the ethicml lab sessions or in the pub with a beer, whichever is the best way for you to spend your evening. So just looking back over the previous questions, Anton had a comment asking about ZB on slide 122. So if I share my screen again, we'll take a quick look at that, because maybe maybe I didn't explain it well, in which case hopefully Thomas can jump in. Okay, here. So the question is around this ZB part. How do you choose the size of it? That is a very, very, very good question, and something that's quite pertinent. Thomas, I'll throw you in at the deep end here, because I know that you have written a short algorithm on the best way to do it.
Yeah, we never found a perfect way to choose the size. You have to try it out. But it's probably relatively small. So if you have an image of 64 by 64 pixels, that's how many pixels is that? Quite a few. But 4,000. But ZB will only encode, like, should only encode the sense of attribute. So it doesn't need that much information. So in our experiment, it was like fraction of a percent. And so if we have 4,000 dimensions, it was maybe around 10.
Yeah, one thing as well with it is it's relative. It doesn't matter too much if you get down, as long as you're within the right order of magnitude. It's not too much of a problem. So we were using size 12, I think, because it was easier percentage-wise to write that. But we did an ablation study trying different sizes of S, and the difference between a size of 10, 20, 30 was negligible. It was such a small percentage of the overall. So yeah, unfortunately, it's a little bit of trial and error. It's another hyperparameter. Generally start very small and maybe increase by an order of magnitude and see what the effect is, and then if there's a big difference, head back down and maybe try a sort of binary search approach, but starting at a very low number.
Yeah, you can tell if it's too large or if the image is completely changed. Like, even if you have no idea what gender in an image looks like, you will notice that the image is completely changed, then you know it's too large.
Yeah. Next up, can you give examples of fairness in healthcare? Well, I can. So I actually know one, but I don't know of any So I don't have much to do with machine learning in healthcare generally. But I know that one of the things that people think of when they think of the symptoms of a heart attack is shooting pain in the arm and a tightening of the chest area around the heart. Those are the symptoms that we're often told about. And those symptoms are far more prolific in men. When a woman experiences a heart attack, those symptoms aren't necessarily going to align exactly. So even just in the way that we generally speak about healthcare, there's definitely a disparity. And if there's one just generally in how we talk and how we teach about healthcare, this will certainly be reflected in models that train from that data. Thomas, do you have anything to add on this topic? No.
I've worked with some health devices before, but the topic didn't specifically come up. But I can imagine lots of places where it would come up.
I think anywhere where you're looking at any decisions and building systems based around people, the concept of fairness and bias and unintended connections in your data, it should be very much at the forefront of your mind. So whilst we don't have exact experience in healthcare, this would probably be one of the first things I'd be thinking of in that area. But then again, as somebody who works in fairness, almost every area that I come across, I think of fairness first. I'm just going through the questions, just having a look at them. I'm fairly certain either everything was answered, or you, Thomas, kindly added slides in the break to make sure that people's questions were answered in more detail, which is absolute superstar behaviour. I, on the other hand, went and had a cup of tea and a biscuit.
Well, wasn't there a question about continuous?
Yes, so that came in earlier on, but kind of missed it. Let me have a look. I can't see it now. It was there definitely, because we, yeah. Anton asked earlier, can you say a few words about fairness metrics for continuous sensitive variables? You spoke for a while on this, but do you have anything to add?
No, maybe just that there are very few papers that deal with this. I think I know maybe of 2. So it's definitely not so easy. So the trouble is usually to estimate how, estimate how independent your predictions and S are, which is difficult with continuous variables.
Yeah, I've got to admit, I've not come across too many papers where they talk about it, because when we think about sensitive attributes, I know for a lot of these, we're very conscious that a lot of sensitive attributes about people generally live on a continuous scale or some sort of spectrum. When they're captured, it's often not captured in that manner.
Yeah, that's true. Yes. Yeah, that might be the actual problem, that the data doesn't have it.
Yeah. That is one of the biggest problems generally with this research area, is that getting access to real data, which contains some of the things you're interested in, is very tricky. So sometimes you have to either create some synthetic data, or change your problem slightly to focus on what's in front of you.
Yeah, we're already past 6, so.
Yeah, so thank you very much, everyone. We're going to sign off now. Thank you very much for listening to us ramble on about fairness. I posted earlier on in the Slack channel, if you've got any questions or anything that comes to your mind whilst ever this Slack is active, please feel free to reach out to us. The slides are fully available on predictive-analytics-lab.com/presentations. Please feel free to look at them at your leisure. We'll leave you with the kind of lab exercise to play around with. There's nothing too strenuous in there. It's mostly a chance to kind of explore a little bit. Again, please feel free to reach out to us either via Slack, or if Slack isn't available, via GitHub as well. The project repository is called EthicML, and is something that we both pay a lot of attention to. So if you want to collaborate on anything in that area, please let us know, because that is a project that we're particularly keen on. Unless you've got anything to add, Thomas, I'm going to say goodbye.
No, said it well.
Cool. Thank you so much. Have a wonderful weekend, everybody, and enjoy the rest of the summer school.
Thank you very much.
Thank you.
Дякую, Андріан. Можеш зупиняти все. Можеш просто завершити. Бо ти хост.
Stop recording.
Stop recording, або просто leave і end meeting for all.
Окей.
Дякую. Па-па.